All right, y'all. So let's work through some examples of how to write electron configurations. Okay, so talking through the two different ways, I'm going to be using a periodic table. So go ahead and pull out your periodic table if you don't have that already. And I want to write the electron configuration for tin. So tin is number 50 on the periodic table. So if you go on to look on the periodic table, it's right there. Okay, so pull up your periodic table. Again, two different ways to write this. I'll write the typical, like the typical version, and then I'll write the condensed version. So in terms of the fill order, 1s2, 2s2, 2p6. Again, you look on your periodic table, 1s2, 2s2, and then this whole thing is 2p6. And 3s2, 3p6, you'll see that I'm not thinking too much about where I'm at because I need to get to 10. And so everything has to be filled. Remember, S will have a maximum of 2 electrons, P has a max of 6, D has a max of 10, F has a max of 14. Okay, 3p6 and then 4s2. And once I hit the 4s, I'm actually hitting my d orbitals, and that's 3d10. And then to 4p6. So essentially what I did here was, hopefully you guys can see the periodic table. But so potassium and calcium, that's my 4s. And then I hit my transition elements, and that's my D. And they're 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then I hit my 4p orbital. Okay. And then I go to 5s2. That's my rubidium and strontium. And then 4d10. And then I hit my 5p, but that's where my tin is. And there's indium and tin. Those are just two electrons. Okay. And if you sum up the things, so 2 plus 2, that's 4. And 6, that's 10. Plus 2, 12, 6. If you sum it up, take my word for it, you're going to get 50. Okay, so it will total 50 electrons. And now for my condensed version, it would then be looking at where the closest noble gas is to what it is that you're writing. And hold on. My screen froze, so hold on. Okay, I'm back. So we have our typical electron configuration. So I just wrote all of that out for in terms of fill and not energy level. So the condensed configuration for tin would be, all right, look for where tin is, and then work backwards to find whatever the last noble gas. So that would be your elements in this last column, 8A, find that whatever that last thing was. And in this case, since tin is all the way over here, the last noble gas I come in contact with is krypton. So I put it as krypton. Okay, put that in parentheses. That's where I'm at. And then I go to rubidium, and that's group 5, or period 5. 1, 2, 3, 4, 5. That's 5s2. 4d10. And 5p2. Okay. The way I would write this, so to figure out the number of valence electrons, put it as 4d10, 5s2, put it in terms of energy level. Valence electrons in this case is going to be 4, 2, and 2, and the energy n equals 5. Okay, so that's how I would write the condensed electron configuration. This is typically what I would do on the homework on the exams because it's a lot less intense, cumbersome to write. Okay. Okay. All right, so there is a relationship between quantum numbers and electron configuration. So remember, the quantum numbers tell you where a specific electron is. And so if I look at this electron, for example, or one of the electrons in the 2s orbital for carbon, I can actually tell you exactly what those quantum numbers are. So for example, in the 1s orbital, N equals 1, L equals 0, because it's the s orbital. M sub L has to equal 0, but M sub S can either be plus half or minus half. In this case, we can say that electron has a plus half. Okay? So for another example, hey, figure out the quantum numbers for the last electron to fill in this carbon thing. So like the last electron has to go in the p orbital. N equals 2 because it's an NSP, 2p. L equals 1 because it's in the p orbital, again, the last electron right here. And M sub L would need to be, and this is where, okay. So here's how I'd write out M sub L. So remember, because L is L is 1, M sub L can be -1, 0, and 1. And so this is how I would write it out. And I know that there are 2 electrons that are going in there. Okay. And so remember, based on Hund's rule, I have to fill one at a time. So that last electron is actually going into M sub L 0. And so I can figure out M sub S, it can be plus or minus half, doesn't really matter. I can now figure out the total quantum numbers, or all 4 quantum numbers for the last electron. N equals 2, L equals 1, M sub L equals, right here, 0, and M sub S doesn't matter, it's plus or minus half. Okay, in this case, we're saying it's plus half, and that's totally fine. If you had said minus half, that would be correct too. All right. Here's another question. What is the electron configuration? And then the quantum number of the last electron added to the oxygen atom. The first thing I want to do is write out my electron configuration for oxygen. Because it's just oxygen, I'll write the full one. So it's 1s2, 2s2, 2p, 1, 2, 3, 4. Okay. Or helium 2s2, 2p4. Okay. So the last electron is going to go in here. Because again, we're filling based off Hund's rule. So we have to fill based on energy level and so on. And so the N value for that last electron is 2 for sure. The L value is P, which is SP, that's 1. Okay, so remember SP, D, F, 0, 1, 2, 3. M sub L, to figure that out, I'm going to have it as -1, 0, and 1. Again, each of these things denote orbitals in the p orbital. And I have 4 total electrons that are going here. So 1, 2, 3, 4. My M sub L is -1. And then M sub S, I honestly don't care if you put it as plus or minus half. I would never ask a question where I'm like, I give you all the same N, L, and M sub L, and then the last one is, I'm not going to do that. So it doesn't matter what you pick, just pick one. I'm going with -half in this case. Okay. And that's it.